Hello. Today we're going to be talking about using Newton's laws. And this is how Newton's laws are applied, and we deal with them every day in our day-to-day dealings with physics. This can be found in Chapter 3, Section 3. The first thing we'll like to talk about today is crash test dummies. Well, what do I mean by that? Well, Newton's first law explains what happens to you if you're in a car crash. Remember, we also call the first law the law of inertia. So if the car stops in a crash, sometimes in as little as 1/10 of a second, or 0.1 seconds, do you stop in that time? Well, if you did, you would be actually injured by the fact that you're stopping so fast, which is why older seatbelts are actually kind of dangerous. Sometimes they break the collarbone, crack the chest, influence the sternum and stuff. But newer safety belts, and we've watched a couple of videos, so you know, slow you down. They stop you, but there's like some give to them. And the reason for this is they slow down the passenger by a loosening force. And this reduces the effects of inertia. And if you weren't wearing a seatbelt at all, you would fly through the window because you would continue traveling at the pace that your car was before. So safety belts slow down a passenger by a loosening force, and this takes slightly longer to slow down, so the effects of that negative acceleration are less. Remember, acceleration is the change in velocity divided by the time, and if we can lengthen the amount of time, we reduce the amount of force, because force is mass times acceleration. And if our acceleration is now slower because it's negative acceleration, the force will be less on your body. We also have airbags, and what this does, this puts a deflating cushion between the passenger and an unmovable object, which would be your dashboard, steering wheel, and windshield. And this deflating cushion is almost instantaneously, if you ever look or have a chance to see an airbag, it's got these big gaps or holes and flaps in the back that as soon as it fills up with air, it instantly starts to deflate. And this is, if it didn't deflate, it'd be like hitting like a wall, which would definitely hurt you. So that's why we wear safety belts, and that's why automotive engineers have put in airbags for us. So Newton's second law, we're going to talk about it in relation to gravity. We've talked about air resistance before, and this is a friction-like force that opposes the motion of objects that move through the air. So anytime we have an object flying, this puts a resistance, a friction almost, as if it were, flying through the air, and that's the air particles being parted or separated by whatever object is flying through the air. And we did an air resistance lab. Actually, we did not do that this year. This would have been an instance where we took paper and dropped it, with those crushed or folded up, and look at the different speeds that it takes to fall to the ground. The amount of air resistance on an object depends on the size, shape, and speed of the object. So there's a lot of different factors that deal with air resistance, which is why when you think about fast things that move through the air, they're very streamlined. They have very little resistance because of their shape, versus like, say, throwing a box through the air. It doesn't fly very good because there's all these different things, surface area that the air can push back on. So remember, air resistance is not the object mass, is the reason why feathers, leaves, and other things, paper, that fall slowly. It's not their weight that causes them to fall slowly, it's the shape that they are and that the fact air resistance puts on them. Galileo was the first one that kind of came up with this, and he said if you took away air resistance, a cannonball would fall at the same rate of speed as a feather. I think he used a hammer to talk about it. And we watched it in a video before, and here's a link as well. You can watch an actual link of when they landed on the moon. They dropped a hammer and a falcon feather, and it fell at the same rate because there's no atmosphere, there's no air resistance on the moon. Another thing about the law of gravity is we have a thing called terminal velocity. And terminal velocity is the maximum speed at which an object will fall as it falls through a substance such as air. We see a little picture over here, and we show that a skydiver is falling, and initially he falls very quickly, and there's very little air resistance, but eventually the air resistance and the acceleration of gravity are balanced out, so he doesn't reach any faster speed. He's at a certain speed. And then if he deploys the parachute, there's obviously a great amount of air resistance, so that force is greater pushing him up, which slows his fall of gravity down. But after the parachute's deployed, then the rate at which gravity pulls him down and that the air resistance is effect, it's a lot slower, which is why when you land with the parachute, you're not falling at the same speed, which means you get injured. So again, the terminal velocity is the maximum speed an object will reach when falling through substance such as air. So the force of air resistance equals the force of gravity. When that happens, velocity is constant. Free fall, the definition for free fall is when gravity is the only force acting on an object. So that's basically, for instance, if you drop something and it falls out of your hand, that object is now in free fall because gravity is what's pulling you down. Okay? And this happens when you're falling in a vacuum because there's no air resistance being pushed up on you. In free fall, you would also constantly accelerate due to the accelerating force of gravity. Remember, gravity is a force, which is mass times acceleration. So objects in orbit, if an Earth did not have a velocity perpendicular to the gravitational force of the sun, it would fall into the sun. So what that basically means is the Earth itself has velocity. And because it's flying at a certain velocity, it's constantly falling towards the sun, but because of its forward velocity, it's constantly falling and missing. And then it just kind of, you imagine it just keeps going around and around because it's constantly trying to fall into the sun, but because it has a velocity behind it, it keeps moving. And there's no resistance to the Earth turning in space, so it will continue to maintain that speed, which is why the Earth's orbit hasn't slowed down and has fallen into the sun since then. Okay? What is weightlessness? Weightlessness is when an object experiences forces that counteract the force of gravity. For instance, if we're standing in a free-falling elevator, or you've been in a car that goes over a really sharp declining hill and you'll feel that lightness in your stomach or in the seatbelt, the objects in your car kind of float up. That's what we're doing is weightlessness. We're falling at the same speed that gravity does. And if you were standing on a scale, for instance, in that, you would notice that the scale would go to zero because you are falling at the same speed gravity is pulling you down. So therefore, nothing's pulling you down. So you'd be weightless. And this is also what happens to astronauts in space, as they are actually free falling toward the Earth. And the same concept that the object falling is falling towards the gravitational, but they also have a velocity because the spacecraft they were in has a forward velocity. So when they exit the spacecraft, they're still traveling at the same velocity as the spacecraft. If they didn't have that forward velocity, they'd get pulled right down into the gravity well of the Earth. So here are some equations we want to know. Remember, we talked about this one, h equals 1/2 gt squared, t squared. What this basically means, you can use this to figure out how high you are up on something. When you drop it and you count the seconds that it takes to hit the ground, we just take 1/2 times the constant of gravity, which is 9.81, times the time that you counted squared, and that gives you the height. And then also velocity, you can tell how fast something is going. That penny or that rock, when you drop it, you count how many seconds it hits the ground, multiply that times gravity. That would be the meters per second that object is traveling when it hits the ground. Let's talk about centripetal forces. We mentioned these earlier. We're talking about and the different things, the change of direction, but not changing your speed, which also changes your acceleration. The centripetal force is the force exerted toward the center of our curved path. This is planets orbiting the sun. Your amusement park rides, they use the centripetal force. If you're spinning around, right, you're accelerating towards the center, and the centrifugal, the push, the inertia, the momentum that you feel, pushes your back up against the wall of the ride. Also works as a car rounding a curve. The car wants to take a straight path. We are accelerating towards the center. We're turning towards the center. And so there's a force due to the friction on the road that keeps us on the road. If we didn't have any friction, say it was icy, we'd slide off. We would take a straight path from the moment we lost friction. All right, so again, friction keeps tires between the tires and the road, keeps traction. And if we lost that traction, we would go into a skid. So if it's a slippery surface or if we're traveling too much speed and that force overcomes the force of friction because of our velocity, then we would lose traction and slide. Let's talk about force and momentum. So we can rewrite the F equals ma using our acceleration formula. We can look at mass is our change in velocity minus final velocity minus initial velocity divided by time. And if we change it and we change velocity, we put our mass up there as well. So we have mass and velocity final minus the mass velocity initial divided by time still equals our force. And so what we're doing is we're trying to get, remember, momentum is mass that's moving. It's moving mass, and that's what we have here. So we can actually use this to tell how much momentum and force objects have. So the collisions between objects, this also deals with Newton's second and third laws. Because remember, second law is force equals mass times acceleration. And then collisions are for every action, there's an equal opposite reaction with the third law. In the conservation of momentum, it says that if no external forces act on a group of objects, their total momentum does not change. And we can look at this when you use a cue ball to break open a rack when you're playing pool. You really have to put some speed and force behind that cue ball if you want this rack, this triangle of other balls, to spread out. And if you don't hit it very hard, that momentum, that one ball has all the momentum that breaks all these other balls apart. And so each individual ball gets a piece of the momentum of the cue ball, which is why you want to make sure you have a lot of force behind the cue ball when you're breaking in pool. And that's it for using Newton's laws.